Hello everyone. Today we shall talk about design criteria for geotextile filters. See, as we know that geotextiles are used for different functions. For example, hydraulic functions, which includes drainage and filtration. Mechanical functions includes separation, reinforcement, and protections. So here, what we are going to talk today, design criteria for the geotextiles if it is used as a filter or filtration, right? The soil geotextile filtration mechanism is a complex process which depends on physical compatibility between the geotextile and the soil to be retained. So it is a complex phenomena, and its compatibility depends upon geotextile and the soil. These two important things are there because geotextile is going to use as a filter, right? And soil has to be retained. Geotextile often perform well under a steady state condition like those found in dams. However, when the soil geotextile interface is subjected to a dynamic loading, the requirements for successful filtering are uncertain and conservative as the controlling factors are not well understood in these circumstances. In its application as an alternative to aggregate filters, as we know that the aggregates or the coarse grain soils are used as a filter materials. So as an alternative of these coarse grain materials, the geotextile are used as a filter. The role of geotextile filter is to permit free flow of water without significant loss of soil particles. So whenever we are going to use the geotextile as a filter, it should retain the soil. Soils at the time of filtration, soils should not pass through the geotextile materials. Therefore, to work as filter, geotextiles should be designed to meet the following four criteria. So whenever we are going to design the geotextile to work as a filter, in that case, four criteria should be met. What are the four criteria? First criteria is the geotextile should have retention capability, the ability to retain soil. The geotextile should have ability to retain soil. Next is the permeability criteria. The geotextile should have ability to pass soil water. Next is the damage criteria, the ability to resist mechanical stresses. And the fourth one is the durability criteria. The geotextile should have ability to last for the lifetime of the structure. So let us begin one by one from the retention criteria. Retention criteria consist of two things. When there is a flow of water, that means whenever we are going to use as a geotextile sheet or materials as a filtration or for filter purpose, right? That means what? Geotextile should have ability to retain soil, only water should pass, right? Soil should be retained. So two conditions are there. One is called a steady state flow condition. What is a steady state flow condition? It is defined as the flow condition under which the pressure at any point remains constant over time at the time of filtration. Pressure remains constant over the time. It is not going to fluctuate. Whereas in case of dynamic state flow conditions, the pressure may fluctuate with even at the constant time, or the fluctuation will take place in case of dynamic flow. So here, what is the conditions? AOS, apparent opening size, or O95. O is nothing but opening size of the geotextile. O95 should be less than equal to B85 swell. What is it? What are these things? Let us see. AOS is the apparent opening size in millimeter. O95 opening size in the geotextile, for which 95% are smaller in millimeter. AOS apparent opening size is also called as O95, right? It is the opening of the geotextile materials. We have already studied the D60, D10 in case of particle size, coarse grain soil analysis, particle size analysis, right? So what is B? B is a coefficient. It is a dimensionless parameter. And D85 soil particle size, for which 80% are smaller in millimeter, right? So here O95, D85, right? O is related to opening size of the geotextile, whereas D85 is related to particle size, soil particle size, and B is the coefficient, right? So this is the equation we can see. Now, the coefficient of B, which we have seen in the previous slide, often varies from zero point 0.5 to 2, but B depends upon different things: the type of soil to be filtered, its density, coefficient of uniformity. If soil is granular, coefficient of uniformity, as we know, it is equal to D60 divided by D10, right? B also depends upon the type of geotextile, whether woven or non-woven geotextile, and the flow conditions. Flow condition means whether it's steady flow conditions or dynamic flow conditions. So B depends upon these parameters, but it varies in between 0.5 to 2. Now we can see, whenever we are going to retention criteria we are discussing, when we are going to retain using the geotextile as a filter for the soil, if the soil is, for example, let us see sands, gravel sands, silty sands, and clay sands, right? But what is the condition? With less than 50% passing 75 micron sieve as per the Unified Soil Classification System. That means more than 50% are going to retain on 75 micron sieve. So what are the soil? Sands, gravel sands, silty sands, and clay sands. So retention criteria means the ability to retain the soil, and the soil should be 50%, less than 50% passing 75 micron. That means more than 50% are going to retain. And here in this condition, B is a function of the coefficient of uniformity, because you see all these are comes under the coarse grain soil, right? Clay sands and the silty sands are there. These are the coarse grain soil, and it is going to retain on the 75 micron sieve more than 50%. So here B depends upon, or B is the function of coefficient of uniformity. Here is you can see for B what value of the B can be used. For that certain conditions are there, certain criteria are there. What are the criteria? If Cu less than equal to 2 or Cu greater or equal to 8, in that case B we can use 1. When Cu is found in between 2 and 4, in that case B we can use 0.5 Cu. If Cu is found in between 4 and 8, then B will be equal to 8 by Cu. Cu nothing but D60 by D10. So for silty and clay soil, that means more than 50% is going to pass through 75 micron sieve. More than 50% pass means less than 50% retaining. So in that case, B can be used as a function of the type of geotextile, whether it's a woven geotextile or non-woven geotextile, right? Here you can see the values of B is going to change depending upon the type of soil to be retained by the geotextile filter. So for woven, B will be 1, and in case this is the equation where B we can put the 1. For non-woven, B we can put 1.8 in this equation, and for both woven and non-woven we can use directly 0.3 millimeter. O95 less than equal to directly 0.3 millimeter. Okay, so these are the conditions and the criteria for the steady state flow. Dynamic flow conditions, what happens here? If the geotextile is not properly wetted down and in close contact with the soil to be protected, or if dynamic, cyclic or exciting loading conditions produce high localized hydraulic gradients, then the soil particles can move behind the geotextile. These things will occur. Thus, the use of B is equal to 1 is not a conservative, right? If you are going to use B is equal to 1, it will not be considered a conservative because the bridging network will not develop and geotextile will be required to retain, even finer particles can be retained if you are going to use B as a 1 in case of dynamic flow conditions. When retention is the primary criteria, in that case B should be reduced to 0.5. Okay, so in this equation in place of B we can write 0.5. Here what it says that dynamic flow condition can occur in pavement drainage applications, whereas steady flow conditions occurs in dam, in case of dam, which we have seen in the previous slide. For reversing inflow, outflow or high gradient situation, it is the best to maintain sufficient weight or load on the filter to prevent particle movement. That's why you can see here it is written, if geotextile is not properly weighted down, that means we have to use the sufficient weight of the geotextile, right, or as a filter. So let us see the next things. Next criteria, the first criteria was the retention criteria. Then the second criteria is the permeability criteria, the ability to pass soil water. That means geotextile should have ability to pass the soil water. You can see in case of permeability criteria, normally two parameters are measured. Water through pass water flow through a geotextile is measured by two test methods in this criteria. So we can also use perpendicular water flow, and the next one is the permittivity. So these two tests has to be carried out on the sample of a geotextile materials in the laboratory, which are similar. The test is similar, but not identical methods. We see perpendicular water flow method is followed by the ISO, International Standard Organizations. These are the methods, these are the codes by which we can test we can go the perpendicular water flow test for testing perpendicular water flow. This comes under by this code actually. This code follows the perpendicular water flow testing for the permeability, right? So this test method for measuring perpendicular water flow or water flow normal to the plane. You can see this figure. This is a geotextile sample. Water is going to pass through it, right? And again outflow is also there. This is the hydraulic head. Okay, so here normal to the plane. This is the geotextile sample. Normal to this plane, the water flow is taking place. So test method for measuring perpendicular water flow normal to the plane is defined by En ISO 11058, and the test method is effectively the same as ASTM D4491 permittivity. So these both the test method are similar. Why it is similar? Because in both the cases the flow of water is the normal to the geotextile plane, normal to this geotextile sample, right? But this is the American method. This is the ISO method. Both the methods are different, right? Both methods are different. So what is the difference? We can see, but the difference is the perpendicular water flow. Here, perpendicular water flow and permeability, both some difference are there. The perpendicular water flow is followed by EN ISO 11058, whereas permittivity is followed by STMT 4491. So what is the difference? Perpendicular water flow is defined as the flow rate in liters per second divided by the area of the geotextile tested, but not divided by the hydraulic head. EN ISO also uses a hydraulic head of 50 mm for testing, and result is presented by velocity. Here, whenever we are going to follow the EN ISO 11058 method, which follows the perpendicular water flow, in this case, to fulfill the permeability criteria, we have to measure the velocity in the laboratory, which is equal to flow rate divided by area of the geotextile sample, liter per second divided by meter square, which will be equal to liter per meter square second. So a permittivity method is followed by ASTM D4491, is a method most commonly used in the United States. So as we saw in the previous slide, perpendicular water flow or permittivity both are measured by the different different codes we can see. So here permittivity is defined as the flow rate in cubic meter per second divided by the area of the geotextile tested divided by the hydraulic head, specified by hydraulic head of 50 meter for the testing. Here, what is the similarity in between the perpendicular water flow and the permittivity? In both the cases, the water flow is normal to the plane, right? In the permittivity test. That's why in the previous slide it was written that both the test method is similar, but the codes are different, used by the different. For example, this one is used by the United States, and the ENISO code is used by the International Standard Organizations. So we can see here, permittivity is the measure of the rate of water flow perpendicularly through a geotextile as shown in figure, and it is defined as permittivity is denoted by psi divided flow rate divided by area of the geotextile multiplied by hydraulic head. So finally it will come per second, right? So psi is denoted by permittivity, and Kn is nothing but cross plane permeability coefficient. Tg is the thickness of a specific normal sheet. This is the thickness Tg. So psi is equal to permeability divided by the thickness of the geotextile materials. So permeability, that means cross plane permeability coefficient in meter per second, we can write psi into Tg. So permeability criteria we have seen in these slides that in some codes use the velocity and some codes use the permittivity. For example, the STM D4491 use the permittivity. So these two tests are required to fulfill the permittivity criteria. Now next we can see damage criteria. Damage criteria, the ability to resist mechanical stresses. Whenever we are going to use the geotextile as a filter materials or as a filter, in that case it should also fulfill the damage criteria. So two types of damage in geotextiles are found to be occurring when used as a filter. The first one is the puncturing of geotextile during placement of riprap. Riprap is nothing but it is a stone or rock pieces on the geotextile and tearing. The puncturing and tearing. Tearing, that means when a stress level adjacent to the puncture exceeds its tear resistance, then the tearing will take place, right? We can see figure shows a geosynthetic puncture test in which piston is pushed into a clamped geosynthetic sample until it breaks. You can see this figure puncture test here. Puncture test, we can see this is a geotextile sample, and it is pushed in downward direction until it breaks. So how much FP we are going to get, that is the puncture resistance values. So puncture strength of the geosynthetic, the maximum load is the puncture strength of the geosynthetic. We can find out FP, puncture strength. Similarly, the trapezoidal tear test, as shown in figure here, is applicable to woven and non-woven geotextile, but not the knitted geotextile. Whereas the tongue tear test is applicable to all geotextile. Here we can see the geotextile sample has been placed in between the two clamps, and the forces that are applied in upward and downward directions, right? And then the values, whatever the force we are going to find in during the test, that is the tear test, or the tear force, we can say, to fulfill the damage criteria. So puncturing and tearing, these two tests has to be performed to check the damage criteria of the geotextile. So next we can see here, for non-woven fabrics, the minimum requirements of puncture resistance and the tear resistance, the very important things. Whenever you are going to use the non-woven fabrics as a geotextile materials for filters, what should the minimum requirements to resist the puncture as well as the tear? So these are the two minimum requirements we shall see here, can be put as below when rubble or rock is directly placed on the geotextile. So puncture resistance or tear resistance. To fulfill these two things, that means whenever you are going to directly place the rubble or rock on the geotextile materials which are non-woven, in that case we have to use this formula. So U is equal to 1050 into H to the power 0.5 D85. U is nothing but mass per inch area of the geotextile. So these are the requirement, these are the condition which should be fulfilled to maintain the puncture and the tear resistance. So U should be equal to this much. Okay. So what is the U? U is the mass per unit area of the geotextile. H is the height from where the rock is placed in meter on the geotextile. In D85, characteristic dia of the rubble or rock layer put on the fabric in meter, and F is the tear strength of the fabric in newtons. So tear strength and the puncturing resistance can be met if you are going to uh, use this formula for the non-woven fabrics. You can see U should be equal to this. So F is the tear strength for D85 less than 0.1 meter. We have to use this formula. This formula we can use to calculate, right, the puncture resistance and the tear resistance. With this formula we can utilize to calculate the resistance. So this formula F is equal to 750 into D85 to the power 0.45. For D85 less than 0.1 meter, in that case we can use this formula. And F is equal to 1500 into D85 to the whole to the power 0.75. For D85 greater or equal to 0.1 meter, we can use this formula. So tear strength for a non-woven fabrics, we can find out by this formula. So minimum requirements of the puncture resistance and the tear resistance can be put as below when rubber or rock is directly placed on the geotextile materials. So these two formula we can use to calculate the tear strength, right? And you can mass per unit area we can also calculate by this formula. So now what it says that a small layer of nearby available sand over geotextile can improve the efficacy of the fabric. Whenever you are going to control the damage criteria, it is always better to use the local sand, right, over the geotextile. Then you can put the gravels on the textile, on the geotextile, right? So these are about the damage criteria. Now we can see durability criteria, the ability to last for the lifetime of the structure. So the geotextile should also meet the durability criteria. So in case of geotextile, the durability is determined mainly by the resistance exerted by the constituent fiber to the environment conditions. That means whatever the fibers we have used in manufacturing of geotextile materials or geotextile sheet, right, should be resistance, should have resistance. That means durable. It should be durable and it should have capability to resist or to bear the environmental problems. So what are the environmental problems or environmental factors or conditions which should be considered for the as a durability criteria for the geotextile? The major environmental factors to be considered are temperature, exposure to UV radiation, pH, humidity, and chemical condition of the soil, and the construction materials of the geotextile, right? So these are the environmental factors which are going to damage the geotextile sheet, right? So this will cause the, or we can say these will damage the geotextiles, right? And we have to we have to manufacture the geotextile sheet in such a way so that it will be durable and it should resist these environmental problems. So for durability, geotextile must be resistant to chemical. These three conditions should met by the geotextile sheet. Then only it will be durable. Chemicals, biodegradable, biodegradation, and ultraviolet lights. So for this, it is always better to manufacture the geotextile sheet to be durable and to act as a filter materials or a filter if it is manufactured by using the polypropylenes and polyester, right? Used in manufacturing of geotextile have good resistance to chemicals, biological and UV light degradation. So these problems can be taken by the geotextile if the geotextiles are manufactured using the polypropylenes and polyester. So these problems can be solved. These problems can be resisted by the geotextile sheets, okay, and it will become durable. The geotextile filters are exposed to sunlight. Some additional suggestions are also given here. If geotextile filters are exposed to sunlight, in such cases additives such as carbon black or titanium dioxides are recommended to provide the necessary resistance due to UV light. So UV light can be resisted by the geotextile. Geotextiles can become durable if you are going to use the additives carbon black or titanium dioxide. So UV light, it can be, geotextile can be protected from the UV lights. So these are all about the durability criteria. So tomorrow we shall discuss about the next topic. Thank you.